Greetings. My name is Ashwin Maran, and I'm here to present joint work that I did with Jin-Yi on the complexity of counting planar graph homomorphisms of domain size 3. Let M be any symmetric Q cross Q matrix. We can view M to be the adjacency matrix of an undirected graph on Q vertices with edge weights Mij. Now the graph homomorphism problem GH of M is the following problem, where the input is an undirected multigraph G with vertices V and edges Z, and the output is a partition function Zm of G, which is defined to be this expression over here. Now the sum is over all assignments sigma from the vertices to the set 1, 2, 3 all the way through to Q, and the product is over all the edges of M sigma U sigma V. The reason that we are interested in graph homomorphism problems is because many counting problems can be expressed as graph homomorphism problems. For example, the problem of counting the number of 3-vertex colorings of a graph G is GH of VC3, where VC3 is this matrix over here, where all the diagonals are zeros and all the non-diagonal entries are ones. Let us quickly see why this is the case. Let us consider some assignment sigma from the vertices of G to the set 1, 2, 3, and consider any edge u comma v from the graph G. We note that M sigma u sigma v will be equal to 1 if and only if sigma u is not equal to sigma v. Therefore, if we consider the product over all the edges in the graph G of M sigma u sigma v, we see that that product is equal to 1 if and only if the assignment sigma does not assign any two adjacent vertices to the same number. In other words, the product M sigma U sigma V will be equal to 1 if and only if our assignment sigma is a 3-vertex colorant. Now, since the sum is over all sigmas, the problem GH of VC3 is exactly 3-vertex colorants. Similarly, we can show that other problems such as counting vertex covers, counting independent sets, the Ising model, Potts model are all expressible as graph homomorphism problems. Now, Dyer and Greenhill were able to show that for any symmetric Q cross Q matrices M, the problem with 0, 1 values, the problem GH of M can be classified as being either polynomially tractable or Sharpe-Hurd. Later, Bulatov and Groh extended the classification to all non-negative matrices M. And then Goldberg et al. Later extended further to real-valued matrices. Then Tsai, Chen, and Liu extended it again to complex-valued matrices M. So this is what we now know, thanks to Jin-Yi, Tsai, Shi, Chen, and Pinny, and Liu. We know that there is a complexity dichotomy for the graph homomorphism problem GH of M, and the problem is either in P or it's Sharpe-Hurd, with nothing in between. Whether the problem is in P or Sharpe-Hurd can be decided in polynomial time in the size of M. Now the problem that we are interested in now is the planar graph homomorphism problem. In this variant of the graph homomorphism problem, we restrict the input graphs to be planar. For the Boolean domain, i.e. Q equals to, we have the following theorem thanks to Henguo and Tyson-Williams. We know that there is an explicit complexity dichotomy of planar GHM for all 2 cross 2 complex valued matrices. The problem is either in P or it's Sharpe-Hurd. Moreover, what is interesting is that we also know that there exists matrices M such that GH of M is Sharpe-Hurd, but planar GH of M is polynomially tractable. In other words, there exists matrices M such that the unrestricted graph homomorphism problem GH of M is Sharpe-Hurd, but when we restrict the input graphs to be planar, then the problem ends up becoming tractable. Therefore, this dichotomy we know for the planar graph homomorphism problem is not trivially the same as the dichotomy we have for GH of M. However, very little is known about the complexity of planar GHM for Q bigger than 2, even if we restrict M to only be 0, 1 valued matrices. Now this is what our work here is going to begin to correct. Before we proceed much further, I want to talk about the model of computation that we're using here. All the work that I cited previously implicitly assumes that the matrix M contains algebraic values. Now the reason they do that is because that makes it possible for us to represent the entries in the Turing machine model. However, our proof here is analytic, and therefore we adopt a formal, non-constructive method of treating planar GHM for any arbitrary, non-necessarily algebraic, real-valued M. So before we go much further, let's take a look at what the partition function Zm of G looks like for any input graph G. We note that the value Zm of G will always lie in the extension field over Q of the entries of the matrix M. This is simply because of the way that the partition function Zm of G is defined. Now, there is this well-known theorem from algebra that states that if the extension field F takes such a form, then it is a simple algebraic extension of a certain pure transcendental extension field over Q. Now, I want to note that this is merely an existential result. We're not claiming to know what M or beta are. It is possible that given F, we cannot tell what M and beta are. However, the existence is all that we'll need. We can show that planar GH of M is in fact equivalent to the problem planar count M. Now, in this problem, we're given a graph G, and we're also given a number X from the field F. And our job is to compute the number of assignments sigma, such that the product over all edges of M sigma U sigma V equals the number X. As we can see, this quantity over here will always be an integer, and therefore its computation strictly lies within the Turing machine model of computation. Therefore, it is possible for us to consider any arbitrary valued matrix M, real valued matrix M. Now, this formalistic view allows us to consider the problem for arbitrary real valued M. And I want to again stress that when we say that the problem pi1 reduces to pi2, all we mean is that if there is a polynomial time algorithm for pi2, then there exists a polynomial time algorithm for pi1. We do not claim to constructively obtain such an algorithm. However, as we shall see later, this is sufficient for our purposes. Now I want to cite and state our main results here. So the first result we'll prove is that the set of Q cross Q real symmetric matrices such that planar GH of M is not Sharpe-Hurd has measure 0. And then we will also show that given the 3 cross 3 real symmetric matrices, we can classify planar GH of M as either in P or Sharpe-Hurd. So I will first need to make a few definitions. Let's focus on the matrices M with only non-zero entries for now. Given any set A of non-zero real numbers, we will say that the set G1 through to GD is a generating set of A if it turns out that for every element of the set A, there is a unique sequence of integers E1 through to ED such the product GI to the EI is equal to plus or minus A. Now, it is known that given any Q cross Q matrix M with non-zero entries, we can find a generating set for the entries of the matrix M. In other words, given any entry Mij of M, we know that there exists a unique sequence of integers such that Mij can be expressed in this form. Now we're going to use this to define this function calligraphic M. This function M is going to take in d real numbers P1 through to Pd, and its output will be a Q cross Q matrix. Now the ijth entry of this Q cross Q matrix will be this expression over here. Now let's note that if we plugged in the real G1 through to GD into this function, then what we'll get is exactly the matrix M that we started out with. Using some well-known techniques in the literature called interpolation by thickening, it is possible to show the planar GH problem of M of P reduces to planar GH of M for all P in Rd. This allows us to prove our first hardness lemma over here. We're going to use the lemma that I just showed, as well as the fact that planar GH of the Q vertex coloring problem is known to be Sharpe-Hurd. If you take a look at the matrix QVCQ, you know that all the diagonal entries here are zeros, and all the non-diagonal entries here are 1. So what we can show is that if we have a matrix M with only non-zero elements in it, that is generated by the set G1 through to GD, and if it is also the case that for every diagonal element M1 MII, there is some GTI in the set over here that divides the diagonal element but does not divide any of the non-diagonal elements, then we can find a reduction from planar GH of VCQ to planar GH of M. And since we know that planar GH of VCQ is hard, this then implies that planar GH of M is hard. So we will now use the first hardness lemma to prove that a larger class of matrices also are hard. In order to do that, we'll again need one more definition. We will say that a set of non-zero reals x1, x2 through to xd satisfy the lattice condition if it turns out that for any integers e1 through to ed such that their sum is equal to 0, we have that the product of xi to the ei equals 1 if and only if all the integers ei are 0. And we will then use, again, results that are techniques that are well known in the literature called interpolation by stretching to prove this following lemma. We can show that if the eigenvalues of the matrix M satisfy the lattice condition, then for any diagonal matrix delta, planar GH of H delta H transpose reduces to planar GH of the matrix M. We will now use the lemma that I just showed as well as the first hardness lemma to prove our second hardness lemma. We will consider symmetric matrices M that have only positive entries and whose eigenvalues satisfy the lattice condition. For such a matrix M, we will now pick a kappa that is transcendental to the field extension over Q of all the entries of the matrix M. Then we will let delta to be D plus kappa I. Now we can easily verify that the matrix H delta H transpose will end up becoming just M plus kappa I. Now the reason this matrix is interesting is because we have a kappa term that appears only in the diagonal terms. And because of this matrix will satisfy the conditions of the first hardness lemma. And therefore, we have the second hardness lemma over here, which states that if M is a full rank matrix with only positive entries whose eigenvalues satisfy the lattice condition, then planar GH of M is sharply hard. Now this directly allows us to prove our theorem here. We can prove that the set of Q cross Q real symmetric matrices M such that planar GH of M is not sharply hard has measure 0. Right. Now we can try to come up with a dichotomy for all 3 cross 3 matrices. We will first consider positive valued full rank matrix M. We can define a function which is slightly misleadingly also called M, which takes in one real and outputs a 3 cross 3 matrix, such that planar GH of M of P reduces to planar GH of M for all P and R. Crucially, this function M of P will satisfy these two properties. The ijth entry M of P will be equal to P to the xij for some non-negative integer xij. Moreover, there will exist some epsilon which is positive, such that for all P within the interval 1 to e to the power epsilon, the determinant of M of P is not 0. Now, we can define the eigenvalues lambda 1, lambda 2, lambda 3 as functions of P, such that within the interval 1 to e to the epsilon, they are ordered in increasing order of their absolute values. With this done, we can now define a crucial function T of P to be log of lambda 2 of P divided by lambda 3 of P divided by log of lambda 1 P divided by lambda 3 of P. We notice that we defined M of P to have only positive values. Therefore, by Maran theorem, we know that lambda 3 of P is strictly larger than the absolute value of lambda 2 of P. Therefore, the denominator over here will not be 0, and therefore T of P is well defined. And more importantly, it is also a continuous function within the range 1 to e to the epsilon. What is interesting about T of P is that it is the unique function that satisfies this equation over here, of lambda 2 being equal to lambda 1 to the t and lambda 3 to the 1 minus t. Now, if it turns out that there is some r within our interval 1 to e to the epsilon, such that t of r is irrational, then that precisely corresponds to M of r satisfying the lattice condition, and thus the conditions of the second hardness lemma. Now, we also note that since T of P is a continuous function, and since irrationals are dense, we can use the intermediate value theorem to conclude our third hardness lemma over here, which states that if the function t within the range 1 to e to the epsilon is not a constant function, then there must exist some r within that range, such that planar gh of m of r is sharply hard. Now I want to note that our choice of r here need not be algebraic, as it comes from the intermediate value theorem. And this is why we had to do the work we did earlier to establish that our model of computation was valid. Now, again, we'll note that we defined the matrices M of P by defining the entries in terms of the function P. But T of P is defined in terms of the eigenvalues of the matrix M of P. And we have very little control over the eigenvalues as a function of P. So what we're going to do now is we're going to study the behavior of the function T of P as P converges to 1. And we will repeatedly use the fact that any symmetric polynomial in lambda 1, lambda 2, and lambda 3 will be a polynomial in P. So using the fact that I just mentioned, it is possible to show that as P converges to 1, T of P will be either 1 over 2 or it will be 1. Now, from the third hardness lemma, we know that if T of P is not a constant, then planar gh of m is sharply hard. And combining that with this lemma, we can show that unless T of P is the constant 1/2 function or the constant 1 function, planar gh of m must be sharply hard. And it also can be shown that if T of P is in fact the constant 1 function, then using the second hardness lemma, we can show that planar gh of m of P is sharply hard. And since planar gh of m of P reduces to planar gh of m, that also implies the hardness of planar ghm. Therefore, all we need to worry about is the case where T of P is the constant 1/2 function. In that case, in order to deal with the absolute value of the eigenvalues, we're going to first define mu I to be lambda I square. And then we'll define the symmetric function f to be this. Notice that since f is symmetric in mu1, mu2, mu3, we can express it in terms of the elementary symmetric polynomials. And that is what we've done here. We can show that f of p equals s1 cubed times s3 minus s2 cubed, where s1, s2, s3 are the elementary symmetric polynomials. Now the thing to note is that the elementary symmetric polynomials of the eigenvalues of the matrix M can also be represented in terms of the entries of the matrix M. And in fact, they are going to be polynomials in the entries of the matrix M of P, and that makes them polynomials in P. So f of P is now a polynomial as a function of P. And we also note that because of the way we defined f, T of P being the constant 1/2 function is equivalent to f of P being the constant 0 function, which in turn is equivalent to the polynomial s1 cubed times s3 being equal to s2 cubed. Now, since they are polynomials, we can use the unique factorization of polynomials to prove that there exists some function f of P such that s1 times f equals s2 and f cubed equals s3. Now we know what s3, s1, and s2 look like, and we know that s3 is equal to determinant of m of p whole squared. And we also know the structure of this polynomial over here. Therefore, we can algebraically show that it is not possible for there to be such a polynomial f of p that satisfies these two conditions. Therefore, it follows that it is impossible that T of P is the constant 1/2 function. We can put that all together to prove our fourth hardness lemma, which states that if M is a 3x3 full rank positive real valued symmetric matrix, then planar GH of M is sharply hard. Now we can consider an arbitrary 3x3 symmetric matrix M with real values, and we can show that there must be one of two things must occur. There must either be a 2x2 symmetric matrix M such that planar GH of N is equivalent to planar GH of M, or there must exist a 3x3 matrix N that satisfies these conditions such that planar GH of N reduces to planar GH of M. Now, we already have a complexity dichotomy for this case, and in this case, we've just shown that the problem is sharply hard. Therefore, we have our main theorem now, which states that if M is a 3 cross 3 real valued symmetric matrix, then planar GH of M is sharply hard, unless M takes one of these three forms, and we can verify in polynomial time whether M takes these three forms, and that proves our main theorem. So in the future, we could potentially extend our dichotomy to all complex valued matrices, since our result only applies to real valued matrices. And we could also extend the dichotomy for Q bigger than 3. Thank you very much, and thank you for listening.